Okay, thank you. Yeah, thank you for the invitation and the workshop. So I'm gonna talk about so I was brainstorming with Linus what am I actually presenting here. So the idea was to really go towards explaining the interface from M++, which is a finite element solver developed by the research group of Christian Wieners, my former PhD supervisor, and to talk about the interface to this software. However, I also want to explain at least two-thirds of the talk about what kind of models you can solve with this. I'm going to talk about in particular about acoustic wave equations, and also during my PhD thesis, I developed a UQ library to the finite element software. And I'm going to talk about, in particular, about a budgeted multi-level Monte Carlo method, which I have developed together with Christian Wieners and Sebastian Krumscheid, who is also giving a talk today. And as soon as I have explained you the model and the UQ method, I'm gonna present you towards the end an Umbrage interface to the server and the client, because you can use M++ in both ways. Or at least it's still work in progress, but I will get to the details. Okay, so let's start with the model problem. What can you actually solve with M++? For example, you can solve acoustic wave equations, where you search for velocity and pressure components, such that you satisfy this PDE, this initial data, and this boundary data. And additionally, I'm going to assume that this wave is propagating through random material. So this rho here, that's material density, and I'm going to assume that it's modeled by a random field. And I hope this is somewhat stable in the internet connection. Um, yeah, so this is the wave propagating through this medium, and I used here log normal fields to model rho, and you see the wave is propagating through this material, and well, the behavior seems pretty random. That's a different sample than this one. I just depicted you this sample right here. And the question is, what can we even say about the solution? For example, can we determine the expected value of some quantity of interest, which could be, I don't know, some norm of the pressure, some pressure evaluation in some region of interest? And well, we can simply estimate this with the Monte Carlo method. But as you can assume, this is going to be very costly, because the simulation of one of these PDEs is already pretty costly. And simulating this multiple times is probably going to be too much. Additionally, there are multiple sources of errors in the simulation. So there's this input error stemming from the random fields when I'm sampling from the random fields. I have discretization errors from the time stepping methods and the space discretization, and also a bunch of other error contributors. I'm mostly going to focus on these two guys. And the goal is to find a combination of methods. So really to search the space of methods to minimize the total error. And this is also happening within the constraint, which is that we only have finite computational capacities. So we only have finitely many CPUs, finite computation time, finite memory. And I'm gonna show you a method which is incorporating these bounds, basically, or this budget, and minimize the error within this budget. So the method of choice is multi-level Monte Carlo. There are some assumptions which are usually true for if you use finite element methods, at least for this method. And then the idea is to expand this expectation value here with a telescoping sum and estimate each of these expected values here with its own Monte Carlo method. So you have this multi-level estimator, and to give you a graphical interpretation of that, you sum up solutions on the lowest level, and then you sum up solutions of this level difference here. That's this y, and this the joint of all these simulations. Joining all these simulations gives you the multi-level estimator. And in 2008, Michael Giles proved the following theorem, that there exists a sequence of samples such that I can choose some prescribed error, and my mean squared error of my method is within this chosen accuracy, and I can bound the computational cost by this guy here. And if you remember the first slide, I was trying to do it the other way. I tried to minimize the error within the computational constraint, and this is somewhat the opposite. I minimize the computational cost within the error constraint. So this led me to develop this budgeted multi-level Monte Carlo method. So I'm going to replace the accuracy epsilon by this budget, which is measured in CPU hours, which is really the key here. The cost measure really is something you can measure on your computer. The motivation is that you often have no a priori knowledge about these rates from the assumptions that you have to choose the amount of processing units and the computational time on your HPC cluster anyways, and that you can do very nice empirical studies of the algorithm combinations. So mathematically, this is formulated as a knapsack problem. So we try to minimize the mean squared error, and we search for the highest level and this level sequence such that we minimize this error under this computational constraint. So the cost of all samples summed up over all the samples and all the levels must be smaller or equal to the computational budget. And then we have this conjecture here, which is that for a feasible and a parallel execution of any algorithm which is trying to solve this knapsack problem is basically bounded by this guy here. So we have a splitting between an error which is basically can only be minimized with further computational time, and one error which can also be minimized by additional computational or by additional processing units. I'm not going to get into the details here, but this is basically the inverted epsilon cost theorem from the previous slide combined with some parallelization laws. I have not told you yet how to actually solve this problem with an algorithm which is obeying to this bound. And usually for these knapsack problems, you use dynamic programming to solve them because they are NP hard, and you need some exploration of the whole solution space, and you better do this in a smart way, otherwise your computational cost is exploding. And you have these three concepts here. You need to decompose your problem into overlapping subproblems. You need to solve each subproblem with an optimal strategy, and you have to reutilize pre-existing results. And then you can use dynamic programming for this approximated knapsack problem. So because we don't have this variance and this expectation here, we also use approximations for this. Okay, so this is the algorithm. Don't worry about it too much. I'm gonna talk later when I'm going to the Umbrage interface about this algorithm a little bit in more detail. But this is basically this dynamic programming ansatz, and to illustrate how this works, I start with an initial estimate up here, and then I'm going to set a new error target, which is basically this dotted line that try to reach this error target. And then I'm gonna set a new error target, which is this one, and I try to reach this error target by basically walking through this sequence of cascading problems. And the nice thing about this plot is you can see this overlapping subproblem structure, and you can also see that this is kind of solved in an optimal manner. I only step as far as I really have to reach the error target. So that's the optimal policy, which is taken from this Acta Numerica article here. And the data structure is basically here, so we don't have to worry about this too much. But you can see the rough idea of the algorithm. Okay, so I have forgotten one little detail, which is very important, namely the parallelization of this algorithm. I call this MS-FEM, so I'm sorry for everyone who is in the multi-scale community. I know there are conflicting names. This MS-FEM stands for multi-sample finite element method. And the idea is to combine multiple solutions of finite element methods into one, basically. So the problem is to approximate m times the PDE on a discretization level, but here again on a fixed set of CPU units. And the optimal parallelization, if I have way more samples than processing units, is simply I distribute everything I distribute all the computations, so these are different samples and the colors are different processes, and I distribute all the computations on different processes. Multi-level Monte Carlo, you usually have this case in between where you have sometimes a few samples less than the amount of processing units, and the optimal polarization scheme to minimize the communications would be to, well, split up the the set of processing units onto subsets and parallelize on these subsets. And this case here in the middle is basically the classical domain parallelization in finite element methods. So again, the idea is to minimize communication, and you basically have to find this natural number k here such that you satisfy this equation. And as soon as you have this k, you know how to distribute your processing units. And on top of this set of meshes, I define this as a set of meshes. I then define a finite element space, and this finite element space then is there to solve for multiple samples at once. That's why it's called multi-sample finite element method. Okay, so back to the model problem and the discretization. So this was the initial problem, the acoustic wave equation, and I'm going to solve this with discontinuous Galeckin in space, implicit midpoint rule in time, and Zircoland embedding to generate these random fields, just to get a rough idea how this is actually solved besides the multi-level Monte Carlo part. And I just show you two little results. So this is the amount of samples over the levels. You see the amount of samples drops. This is where actually the computational benefit comes from. This is the time budget, the red line, and the summed all the computations summed up basically add to these lines. So we see that the algorithm stays just below the time budget. This is alpha and beta, the assumptions, and here you can see some quantities of interest, some estimated quantities of interest with a very small error bar, which is that small because we solve for different problems here in this example. Namely, we solve for different random fields with a different covariance function. So I increased the covariance here, or this sigma squared here, and you see the more variance I tune into the problem, the worse is the error. Basically, that's a pretty natural result, I would say. And the other thing is parallelization. Let's forget about the first result here and just focus on the second one. So as I add more processing units, this algorithm is actually capable to really reduce the error. So the more processing units you can see here, the smaller the error. So that's basically proving or demonstrating that the algorithm scales rather well for more processing units. Okay. So now I'm going to get into the details to the Umbridge interface, which is still very much work in progress. So here's the algorithm. Forget about the details. We are right now here in this MS-FEM routine, I would say, and this is the C++ implementation. I know a lot of boilerplate code in C++, but bear with me here. So Umbridge client, that's basically a CMake configuration. I can compile the code with Umbridge and I can compile it without Umbridge. And when I compile it without Umbridge, I basically use this class here, PDE solver. And this PDE solver is responsible for solving for multiple samples at once. That's why you see here this with COM_split. This COM_split is basically the lower k from the multi-sample finite element method. That's this natural number k. And if I compile the code without Umbridge, I'm just going to run into this. And if I compile it with Umbridge, I'm setting up this Umbridge client. And then there's a lot of stuff happening here. Basically, without Umbridge, I'm just calling the PDE solver to run with some input data, which is basically solving the PDE for multiple samples at once. And otherwise, I'm calling the Umbridge client and call the evaluate function, which you know from yesterday. And I just feed in the input. Okay, so that's the Umbridge client side in the algorithm. And I promised you to also present you the other side, which is the Umbridge server side. So I talked about this PDE solver class already. You see acoustic PDE solver. That's basically the combination of the PDE problem and all the solving methods combined in one class. So that's a composition of solver and problem. And you know that this class here already has this method here, run, which basically solves the PDE. And I just use this simple trick here. I inherited from Umbridge model and acoustic PDE solver. And that way I can just use Umbridge to call the evaluate function, and the evaluate function calls again the run function. So I can really swap out my own code by Umbridge and swap it back in depending on how I compile the code. And all this is implemented in M++, which is the finite element solver of my former PhD supervisor, Christian Wieners. And just roughly the project structure. So here's all the C++ code in the source directory. We have some basic logging and parallelization stuff, some algebra, and then the meshing library, which is basically responsible for distributing all the meshes and finding the distribution within the mesh. And a lot more stuff. And then there's this app, which stands for application. So in this library, the PDE solver classes are basically stored. And this is where we hook in the Umbridge server. And then below that, that was actually my PhD thesis, was developing this additional UQ library for the solver. There we can hook in the Umbridge client. And here is basically this budgeted multi-level Monte Carlo and also some other UQ methods are implemented here. And again, depending on how you compile the code, you can either compile it with Umbridge server, Umbridge client, or without Umbridge at all. And this is all handled by the Docker file in the project root. And the idea is to really go. We've heard yesterday, and I talked about CI. So we use continuous integration for this code here as well. And the idea is to use the CI to produce continuously new images of M++ as Umbridge server and Umbridge client and publish them such that we can easily swap out, for example, the whole finite element part by another finite element solver, or swap out the Umbridge the UQ code by some other UQ code and really have intercomparability between different solvers and UQ codes. Yeah, so that's basically the idea. So this is very much work in progress, and also this part here is still not solved 100%. Communicating this input data, but I hope we will get there soon. Okay, so with that, I guess I have explained the Umbridge interface from both sides, and I just want to give you a short conclusion and an outlook. So we talked about budget multi-level Monte Carlo, we talked about this multi-sample finite element method, and I showed you some simulations for the acoustic wave equation. Further work, we did this for other PDEs. I chose the acoustic wave equation because the images look cool and it's the most challenging problem. But you can also easily do this with elliptic PDEs or transport equations, parabolic or hyperbolic, doesn't matter. Again, so we develop a lot of software in M++. The latest release is 3.2.0. You can find more about this budgeted stuff and what's in progress, this interface to Umbridge. We think about new UQ methods. I'm currently developing this full solution estimator, which should appear in 3.2.1, and some other UQ problems, Bayesian inverse and optimal control problem. Okay, and with that, I thank you for your attention.